Hello there, this is, as you can see, some notes on exponential growth and decay. It says day 2. So the cool thing about this one is that you don't actually have to make calculations for the most part. So as you can see here, really the second question is what we're doing. How do I know if it's growth or decay? By looking at the equation. This one right here, we kind of already did in an exponential growth or decay function. How do I know to add or subtract the rate? So we kind of already looked at problems where we figure out whether to add or subtract, like 1 plus the rate or 1 minus the rate. And then how do I know if it's growth or decay? We've also looked at that, but a little extra time here to make sure you have a fair shot at it. So these notes here, it's definitely what we're doing, but you've already seen this, so skip to problem 1. A study is done on the population of a certain fish species. Suppose the population size after 2 years is given by the following exponential function. Well, as I'm looking at this, I could break it down immediately, but I'll just start looking at the prompts. The initial population size, that's the initial value, which is this number here. So 230 fish initial size, again, as stated earlier. No real calculations needed on this one, mostly just observation and analysis. Does the function represent growth or decay? Well, that's going to come from the rate. The rate is 0.72, and that is going to be decay. Because if you look up here, growth is going to be when your rate of growth is greater than 1, or your multiplier is greater than 1. Decay is going to be when your rate, which here is b, is between 0 and 1. As you see here, this b is between 0 and 1. So if the b value, which again is the value with the exponent, if it's between 0 and 1, it's decay. If it's greater than 1, it's growth. So this growth rate of 0.72 is between 0 and 1, so of course I write decay, and you definitely can read my explanation here. And then just taking that rate and changing it to a percent is all we have to do for C. It says by what percent does the population size change each year? And we're going to take that percent and say each year there's 72% of the population remaining, right? Less than 100, so it should make sense. It's decreasing, so it is decay. This one, suppose the dollar value VT of a certain car that's 2 years old is given by the following exponential function. And here you see it, B of t equals 19,900 times 1.25 to the power of t. Find the initial value of the car. Well, same thing as the last one, right? The initial value is this number here, right? It's like, even if you look back up here, y equals a times b to the x power, you can be reminded that the a value is the number out front here, is the initial value, which is the 19,900 here. And the b value, which is the base of the exponential piece, the b value is the rate of change. So again, down here, $19,900, that's our initial value. This does represent growth as the rate is greater than 1, you guys. 1.25 is greater than 1. And then the car is worth, again, by what percent doesn't change? We're going to just use the 1.25. Make it a percent by moving the decimal 2 spaces right. The car's worth 125% of its previous value each year. So over 100%. And that's kind of how we see growth, as it's more than 100%. Going along here to the next few problems, I'll just explain them, but they are the same. This one is the future price of a certain item. It's given by the exponential function, where P of t is measured in dollars and t is the number of years. So it's, again, there it is, and you can see your initial value and your rate of change. Your initial value being 800, that's this answer, right? The initial value of the item is $800. It is greater than 1 here, the rate, 1.034, so we're going to say that's growth because the rate's greater than 1. And then over here, by what percent? Well, we're going to use the 1.034. And this could be a little tricky, but just try to roll with it and know that, again, all you're doing is moving the decimal 2 spaces right, and that's how I came up with my answer. The price is always going to be 103.4% of the previous value. It's going to be a little more, right? Over 100%, it's growth. Next one, a study is done on the number of bacteria cells in a dish. Suppose population size after t hours is given by the following exponential function. So there it is again, without even looking. Well, we already kind of know what the prompts are by now, but your initial value and your rate. Your initial value says there's 3,200 cells at the beginning, right? So that's our answer. It does represent decay, as you see here, because the rate's 0.91, and 0.91 is between 0 and 1. Again, the rate between 0 and 1, that's the number's going down. It's decreasing. We're calling it decay. And again, moving your decimal 2 spaces right would tell you that the percent by which it's changing, use that. It's 91%, right? 91% of the population remains after each year. And then this last problem here, suppose the future price of a certain item is given by the following exponential function. In the function, P of t is measured in dollars, and t is the number of years from today. So again, here you see it, 1500 being the initial value, as we have that here, initial price 1500. The rate 1.028 it's greater than 1, so we have growth, right, as stated here. And by what percent does the price change each year? And we're just going to use the 1.028, move the decimal 2 spaces right, and say each year the population is 102.8% of the previous year. So hopefully you're seeing some themes here, some patterns where like every time it's growth, it's over 100%, right? It's growing, it's more than the previous. So the only way to get more than the previous value is to take more than 100%. And then also, if it's less than 1, right, it's decay, and your percent is less than 100%, less than the previous total. So hopefully this helps. Thanks for having a look and a listen, and work on some of the practice once you finish this. Thanks. Bye.